Okay, thank you for coming to this discussion session today. Just tell you that you're free to ask any questions you have about the Lab 1, the solution of Homework 1, or the recently released Homework 2. So just let us know, start throwing your questions, and we, the four of us, will try to answer. First question? You want to? Not working.
Yeah, so here we have a function definition. It is Fibonacci numbers, probably you know that. And here we have a sample implementation of it. And the question asks you to draw the data flow diagram of this, right? And here are some nodes that you're allowed to use to solve this question. Okay. Okay, it is. Okay, anyway, I think I can do it one hand. Okay, so we have A and B to start with, and then we will need to do the calculation here, right? And those are the nodes that we have. So initially, we will have 0 and 1 needed, right? And then we will need to add those together to create C. So here we put an addition node, and those two inputs come here. So this is quite simple, right? First three lines represented in a data flow diagram. And then we have here a loop, a while loop that depends on n. And n is an input, an argument to that function, and is being decremented inside this while loop. So we'll also need to implement that decrement operation, right, iteratively. So we can put this here as a separate block, as a separate part of the data flow diagram. And it's basically another addition with a constant input of -1, right? Because we'll subtract it from n. And here the input is initially n. I will show it with capital N here. So let's draw the arrows too. Okay, and the output of this addition will need to be compared against 1. If it's bigger than 1, we will do the operations here inside the while loop. If it's equal to 1 or smaller, then we'll return C. So we also need a comparison node, right? But this comparison shouldn't be here after the addition or subtraction here, but should be before that, right? Because here we first check for n's value before the any subtraction. So it should be, I'm not sure how to draw it nicely, but let's do it like this. We compare against 1, and then so here we'll need a copy node, right? Let's put it like CP, and the CP. Okay, let me draw that part again. So we'll have n. We'll copy this n to this comparison node, which gets -1 on the other side. And then we also copy it to addition node. Is there a question? Yeah, the other one is 1. Yeah, that's true. Okay, we compare it against 1. And here we get some Boolean value as an output. Here we get the next n, right? So this output will need to be connected here, right? So initially, we have the capital N. This is a constant value. And in consecutive iterations, it will be, the value here will be equal to the previous value minus 1, right? We connected it. And then will be copied here to the addition node and the comparison node again. Okay, so we have this Boolean equation, right? So yeah, for every iteration, we have the result here. And then we will need to implement those operations here. So on this part, we already have the first 3 lines. Then if this Boolean value is true, then we will need to do something else. If it's false, we return C. So then we have a branch here, right? So let's implement that branch. So this branch takes the result of addition as one input, and as a control input, it gets this Boolean value. So, so this is not needed anymore. This was the old one. So I will label this as B. This Boolean value that is output of this comparison node will be B. Okay, so just to make the drawing nicer. So the control input is B. And based on the value of B, we will either do something or return C, right? And C was this, the output of this addition. So if it's false, this is the false output. We return this, and the data flow engine returns the value, and it has nothing else to do. If it's true, then what here we need to do is basically adding A and B together again, and then assigning different value to A and different value to B. And it's being subtracted at this part. Okay, so we have C. This C, so this true part is the value of C that we got from current iteration, right? We will need to assign it to B here. So initially, this wire here was representing B with initial value of 1, and this was A with initial value of 0. So this here should be connected to B. Not sure how to draw this. So sorry for the ugly drawing, but yeah, so we connect this, the output of the branch node in case of true, to B here, right? So initially, the token was 1, and then in consecutive iterations, the token value will be equal to whatever the output of this branch node is, right? So we are done with this part here. Then we need to assign B to A, but so B is the current B value, right? So which is basically, we can put a copy node here. Let's draw it like this. And this is the current value, so it is very difficult to draw it, but basically I need to erase something to make it nicer, but so just imagine we have this connected here, and then copy part goes to here, or copy also gets here, right? So this part is getting here, this part is getting here. So anyway, this drawing is too ugly. Maybe we will go over the solutions, but I think you got the main idea. So I think here the problem was the fact that whether we can connect this line here or not, right? Yeah. n minus 1.
Yeah. It's just the first.
N2.
Uh-huh.
The answer is 2, but normally N2 is 1.
No, N2 is.
So do you think the same about the solution that we provided?
Yes.
Okay. Might be better to go over that because it is quite ugly to work with. This drawing. Oh, I also have it here. Okay, so this is relatively nice drawing. So basically here we have the same thing, but a complete thing maybe, and like with nice drawing. So here in this part, you see the calculation of n. Right? For each iteration, we decrease it by 1, and then copy it to different branch nodes here. And then we have A and B initial values, and then the output of this branch goes here, blah, blah, blah. Okay, so let's show some examples here, like to describe how this data flow engine works. So let's assume that we have, let's choose a relatively smaller number for n. Let's execute it for n equal to 3. Is it fine? Okay, so we start here. So basically, when you execute a data flow engine, you should first look at which nodes are ready to fire, right? So here we have, so a node becomes ready to fire when all inputs are available. So this copy node here, for example, has only one input. And initially, we have token with value 1 here, right? So this is ready to fire. But if you look at this addition here, this is not ready to fire yet, right? Because we don't have token on this side. We have only token ready on this side, which is 0. So I will write the ready tokens like this here. And then when a token is consumed, I'll just put a scratch on it. Okay. So here we have a copy node with all inputs ready, right? So we consume this value and copy it here and here. Now this branch has one of its inputs ready, but the other one is not ready, right? So we need to have something here on this wire. But the addition is ready. So we had initially 0 here, and now we have 1 here also. So we can also fire this node here. So if your data flow engine is like working correctly, it's implemented correctly, you should be able to fire any node that is ready at any time. And it should provide the same result. Right, so we do the addition, we consume those 2 tokens, and we have 1 here on this branch, but it doesn't have the other token ready yet. So let's look at this part. So here again we have a copy node with n. So here n was equal to 3 initially, right? So we copy this 3 over here and over here. And this comparison node gets always 1 from one side. So this is kind of different representation here. So this one here means that every time you supply a token 1, right? So probably it was clear in the solution. So it is not that the token available at that time. So basically this is a continuous input of 1s, right? So it's constant 1. Okay, so we are ready to fire this comparison node. We have 3, 1. It produces true, right? Because 3 is bigger than 1. We consume this 3. We also consume the 1, but we have another 1 immediately ready. So we have true here, and we are on the copy node. So this copy node copies to 3 different places, right? So we consume this true. True is being copied here. True is being copied here and here. So we are ready to fire this part. So basically, let's execute this part first. So it would be... So basically, we will be done with this part after showing this. So we have true here. We have 3. We copy 3 over here on the true wire here, right? So we consume this. We consume t, and we have 3 here. We have -1. We add those together. We consume 3, and we have 2 here for the next iteration. So this is a copy node. We have 2, right? So we consume this. Now we consume 2. We copy 2 here. We copy 2 here, right? And then is 2 smaller than, bigger than 1? Yes, it is. We have another 2 here. So at this point, you should be careful because here we can, although all inputs are ready for this copy node, we cannot fire this because we have tokens already available here, which are not consumed, right? So basically, you can fire this depending on your implementation. If you can buffer multiple tokens, then it's fine. You can fire this. But let's now, for this case, assume that we have only buffer of size 1, right? So we can have only 1 token available on the line, and before consuming it, we cannot produce another one. So we are basically blocked on this part now, right? So we have true here, we have a copy node, but we cannot fire this copy node, and we also cannot do anything else. So we first need to consume that part here. So it is how actually in data flow engine we get some kind of a serialization. We put an order between the operations, right? Okay, here we have T and 1, which means we will copy this 1 over here. So let's consume those. We copy it 1 over here. And then okay, we can also fire this node over here. We have true, we have 1. We copy this 1 here. Those 2 are consumed. And then we consume this. We have copy node, copy to here, copy to here. Now we have 1 and 1 here, right? We add those together, and it is 2. Can we fire this node now? Not yet, because we don't have input here, right? But we had true here, which we can fire and copy over here. And then true and 1, again, the same operation, add this again, and this will happen once more. And at the end, what we'll have, I think we'll have 6, right? Do we need to execute the entire thing? Okay, now the sum is here too, right? So we executed this once, so we did the addition operation once, and on the second time, we had 1 on this line, right? We copied 1 over here. Excuse me. Yes, we copied 1, and then we had 1 here. We produced 2, and now this will evaluate true again, and we will copy 2 over here. And in this iteration, 2 will get here and here. Assume that we get here once more true. So we'll get, if n is equal to 3, we'll get 3 times true, right? No, 2 times true. For 3, for 2, and for 1, we won't get true, right? Okay, so we already consumed true once. We will consume it for the second time, right?
But you will do the addition, so it won't be 2.
N plus 1.
I think this now addition is 1.
The answer is 3, but Fibonacci it's always 1 dragging.
So we had 2 here. We have 1 coming from here. When we put those together, we have 3, right?
You give false, so the output will be, I guess.
So is the answer also 3 when this code is executed here sequentially? So what we will have here is, so initially we will have C equal to 1, and then do the same thing again. This is 1 in the first iteration, right? This is equal to 1, this is equal to 1, and in the second iteration, we decrease this by 1. We'll have here 2, we'll have 1, we'll have 2, and then we put together 1. Yeah, this code also gives 3. So if you have implemented this code, Mm-hmm. It skips the top part here, you mean? Yeah. The data flow engine is skipping that?
Yeah, I mean, the algorithm is returning to when you set n to 3.
So when n is 3, this should return, so we enter 2 times, we get 1, copy 1, and get 2. Yeah, right, we get 2 in the code. Okay.
Two times consecutively, but they give the exact same answer. But when we are in the data flow, we just add them 2 times. That's why we make one more addition.
Right. Okay, I see. So here, initially we have 0. We do the addition regardless of the result of this comparison here, right? Exactly. That's the problem. So what could be the fix here?
Increment n by 1 from the beginning.
But then
it's not this algorithm, then it's something else.
yeah. So the problem actually is over here somewhere, right? So this addition should be triggered only in case it should work every time. So this is done regardless of this. But then we should get seems like here we have an issue in this solution. We'll get it fixed, and and also we'll consider that when we are evaluating your solutions. But yeah, you probably hopefully have the right solution in your homework, although you have some small issue here. Okay, so I'll check it again. I'm not fully convinced that we have a problem here, but if you have, you'll release the proper solution, and then you can check and compare it with your own solution. Okay? Anything else? Is that related to this?
The question about the data.
Yeah.
So you said that copy blocks until the previous input, and then the copy outputs the next.
Mm-hmm.
Is that right? So there is this blocking relationship.
Right.
So it's not possible for the left side to overrun, and because the right side takes longer, you'll lose.
Yes. Otherwise, it doesn't make sense, right? Because you have race conditions, and you basically lose some data.
Yeah, I agree. Okay.
So in
just wanted to check.
Yeah. So in real implementation, what you'll have really is you'll have some buffers for input values and output values, right? And depending on the size of this buffer, you can continue executing some part of the data flow. But eventually, you'll need to use all the data produced. And if you override it, it doesn't make sense. Is that the second question you are referring to? So the first one was paper reviews? Okay. Second one. So hopefully all of you remember this question. It is a little bit longer, so it's maybe difficult to, I mean, it will be time-consuming to read this whole thing, but basically what we have is a one-channel, two-rank system, right? One-channel, two-ranks DRAM system, and each channel has its own memory controller. We have 8 banks, and you were asking about the timing diagram. Which part is that exactly? So let's see what it says here in the question. DRAM is refreshed every 64 milliseconds, running by command from the memory, which occupies command bus on the associated memory channel 4 and the associated bank. Okay, so a single refresh command will only refresh a single bank from that rank, right? So that means you can, every 5 nanoseconds, the memory controller is free to issue different refresh command to different bank, or the same bank if it's ready, if it's completed the previous refresh operation, right? So to answer your question, every 5 nanoseconds, the memory, you can expect the memory controller to put a refresh operation to any available bank in any of the ranks available on the system. So so let's say this is time 0, and time goes this way. So if, for example, here until 5, you have a refresh to, let's consider only a single rank, one rank, right? So you refresh, let's say, bank 0, rank 0, bank 0. After 5 nanoseconds, you can also put here another refresh command to refresh bank 1 or any other bank. So you can pipeline those, right? But here, at this point, you cannot refresh bank 0 again because bank 0 is already being utilized. It is already being refreshed. So we should wait 40 nanoseconds. Right. To issue a refresh to the same bank, you need to wait at least 40 nanoseconds. So this is a little tricky, actually. I think it is. So it is tricky, but I believe it is clearly defined here because in C here it says what data bus utilization across all memory channels is directly caused by DRAM refreshes, right? So what you say is kind of an indirect result because DRAM is being refreshed and basically you cannot access this bank, so you cannot read anything out of it. You cannot utilize the data bus. That's true, but it is not directly because of refresh, because the refresh command itself is not using the data bus. Yeah. You only give the address, the bank address, to the DRAM. The memory controller only gives the bank address, and the data bus idle otherwise. So if you have another rank, for example, this data bus can be utilized by the other rank if it's not under refresh. So you can't say that the refresh operation is utilizing the data bus, actually. It may cause the data bus to be underutilized, but it is kind of a side effect. It's not a direct effect. Yeah.
When we issue a refresh command to a certain bank,
so it depends on what kind of refresh command you're issuing. So in DDR3, DDR4, in real implementations, there are bank level and rank level refresh commands. So if you issue a rank level refresh command, all the banks in a rank are being refreshed. So yeah, so the entire rank is unavailable. But if you issue per bank refresh, which is available with DDR4, I guess it's not available in DDR3, then you can access other banks. Yeah. So here in the question, it clearly says that associated memory channel for 5 milliseconds and the associated bank, right? So this means this is a bank level refresh command. Any other questions regarding this one, or any other question in homework 1, maybe? You submitted them.
I reviewed the papers on the hotgraph system and then I didn't put the review here as well because
Yeah, so, yeah, actually, you're right. The reviews are supposed to be only on the system, on the hot CRP system. But if you also put them in the PDF that you submit, it's fine, but probably nobody will look at this.
Sure.
So you should definitely submit it to hot CRP. Okay, if there are not, yeah. Reverse engineering caches. Oh, another tricky question. Okay, so is there any particular part of this question that you were? Part B, cache associated with it. Okay, so in this question, we basically have here many choices of for different properties of the cache, and the question asks us to find which cache is implemented, and we need to find it based on the traces we have here. So here in this table, it shows access pattern A, and so these addresses, blocks at those addresses are being accessed, and as a result of this, those accesses, the hit rate is this here. All right. So the block size is easy. Probably you figured this out. So if you look at access pattern C here in this table, it is quite clear, right? So since we always start with cold cache, so the cache is initial empty, we'll always get a miss for the first access, right? So this is a miss. We know that. And the hit rate here is 4. Some of the addresses here should have hit, right, in order to get 4 out of 9 hit rate. So if we, let's say, assume this is a hit, this is a hit, this is a hit, and this is a hit, we get 4 hits. And if you assume the rest is miss, right, like this, we can easily say that cache block size is 64 bytes. I'm not sure if there's a formulated way to solve this, and you just probably need to think about it. Probably it was easy to figure out, right? Is there anyone that had trouble with solving this part? So basically here we have kind of an exponential increase in the addresses, right? So if you don't get hits here on these parts here, it is clear that you can also get hits here, right? So if the block size is something very small, let's assume it's only a single byte, right? So you'll have all misses. So if you ever gonna have any hits here in this trace, it should be somewhere in the beginning because the address is increasing exponentially. Okay, so it was easy, 64 bytes. We eliminate the other options, and then we have cache size, cache associated, and replacement policy. So here, how I approached this question was, initially I assumed some properties here to be true, and then checked if the access pattern gives the hit rate here on the table. So let's assume, for example, we have one-way associative. So this is direct mapped, right? Direct mapped cache of size 4 kilobytes. So basically, the first property, the first selection here for everything we assume to be the default. And then when you run this access pattern A, you will see that it doesn't give hit rate 1. So then you change something, right? So here, so since now we know the block size, cache block size to be 64 bytes, we can calculate the index, right? So if you have a direct mapped cache, the index will be address divided by 64. So let's write the indices. Can you see this? Okay, I will just write here. So here we had addresses of blocks accessed, and here I will put the indices, right? That indices that we have, assuming the cache block size is 64 bytes. So for address 0 divided by 64, it is 0. So this number here, it is easier to work with powers of 2, actually. So this is equal to 2 to the 12, right? And then 64 is 2 to the 6. If you do the division here, it is 2 to the 6. And then for this guy, it is 7. For this one is it is not divisible, right? Yeah. So it is this, right? Is it true? Yeah. And this is 7, and this is 6 again, and this is 0, right? So this is what we have. So if it's a direct mapped cache, and the size is 4 kilobytes, right, and the cache block is 64 bytes, how many rows we have on the cache? So it is basically 4 kilobytes, again, 2 to 12 divided by 2 to the 6. We have 2 to the 6, 64 rows on the cache. So the cache looks like this. We have some tag here. Right, so we assumed one way for now, yeah. We assume something, and then we evaluate the addresses here we have. If we get the hit rate that is on the table, then our guess was correct. If you don't get it, our guess is wrong, right? Okay, so we have 64 items here. So let's evaluate this one quickly. So we put 0 here on the first row, right? Because 0 mod 64 is 0. And then we have 64 here too. This is again, mod 0 is 0. Then we get another miss. So let's put misses here, miss here, and we replace 0 with 2 to the 6, right? And then we do have 2 to the 7. And this will go again here, right? We will get another miss. So those are all mod 64 equal to zeros. So here, for this one, this goes somewhere else, right? But again, it is a different cache line, so we'll have miss for this too. Yeah.
You didn't divide 3 by 64, so actually that one.
Right. Yeah. Yeah, that's true. That's true. So this is missed too, and this is being replaced. This is also being replaced, right? So we get 0 misses, 0 hits in this case. So one of our assumptions here was incorrect. So since we are having a lot of trashing effect here, right? So we are discarding one of the cache line entries, but in fact we have access to the same cache line here, which is assuming you have 64-byte cache block size. It is the only possibility to get hit, right? Oh, we also have 0. Okay, so you have 2 possibilities. We will get either hit here or here, right? So having a cache line, cache associated of 1 doesn't make sense in this case. We can never get a hit. So if it's 2, so remember that those addresses all go to the same row here when we have 4 kilobytes cache size and associated 1. When we have two-way associativity, then we'll have half of the number of rows. And then again, all those addresses will go to the same row, right? Because if a number, if mod 64 of a number is 0, mod 32 of a number will also be 0, right? So those all go to the same row, and they will discard each other. But this time, since it is two-way associative, we'll be able to keep 2 of these addresses in the cache. So we'll be able to keep this, and then we will discard 0 because it is LRU policy that we assumed, right? So we discard 0, get this instead, and then we discard this, get this instead. So always we have the last 2 in the cache available. So we have these 2, and this comes, we don't get hit. We have this 2 in the cache, this comes. So again, we cannot get any hit, right, when we have two-way associativity. Is it clear, or do I need to go in more detail here? Yeah, so here the takeaway was that all these blocks go to the same row, to the same set of the cache, right, and discard each other. If we have two-way associativity, we can never keep data, all the data here from this point to this point, right, because we can only keep 2 of them. But if you have a 4-way associativity, then we'll have 4 of these values always in the same set. So if we draw it like this, so we have 4 slots available, and we have many of those, right? So we'll be able to put 0 here, 49.6 here, the other one here, and then the other one here. And then this 16K will discard 0 because we assumed LRU policy, right? So it will get here, but the next access is to 4K, to 49.6. This will get a hit, right? And then 0 was discarded, it will get a miss. So in this case, if we assume 4-way cache associativity, we will get 1 hit, as in the table. Okay, so basically, this is the approach that you can follow to solve this question. Make some assumptions. So you have limited number of choices here. If the question was something like, it says that cache associativity can be anything, cache size can be anything, then you need to think about something else. But in this question, since there are too many things that are unknown, and you have limited selections, you can use this approach, yeah.
Could you explain the cache size as well? Because I didn't really get it. In the solution, it says they will all map to the same set, and we already assume 4-way associativity.
Yeah.
So how would 0 be a cache hit on an 8-kilobyte cache?
0 be cache hit for C, you mean for A? For B.
Yeah, but question C.
Oh, okay. Cache size. Okay. So
Yeah, that's the hit. But why would 0 be a hit on an 8-kilobyte cache? The associativity stays the same.
right.
It should be
You think so? So so the associativity and cache size affects the number of sets you have, right? So if you increase associativity, you reduce the number of sets you have. If you increase your capacity and keep the number of weights the same, then you increase the number of sets you have.
Yeah, but in the solution it says they will map to the same set. I think in my solution they map to the same set as well. I'm not sure anymore.
Okay, let's take a look. I have no idea where is the solution for that, but I will just do the solution here. So for C, okay, so let's draw the cache with the information that we already have. So we know the cache block size to be 64 bytes. We know the associativity, it is 4, right? So it is the only associativity that satisfies access pattern A. So our cache looks something like this. Dots here, and here the number of sets, if we have 4 kilobyte cache, will be equal to 16, right? If it's 8 kilobytes, it will be equal to 32. Those are numbers that I remember, but probably it's correct, right? Yeah, so with 4 kilobytes with one set associativity, it was one way associativity, it was 64 divided by 4, it is 16. Yep, okay, so it's correct. So now if you look at B, is it possible to put those together? Okay, so B is there on top. So if we divide those numbers by 64, just to make the math easier, we have, what is this? It's 10, right? So it is 16. We have 32. What is this number divided by 64? 48? Yeah, 48. 64. Is that 80? You were here, right? Yeah, this is 986. And then this was 48, and then this is 0, right? Okay, so this maps to set 0, right? This maps to, if you assume 4 kilobyte cache, this also maps to set 0. This also maps to set 0. All values here map to set 0 if it's 4 kilobyte cache, right? Which means we'll have 4 of these always in the cache, and we need to get one hit at least. So where's the possibility to get a hit? So it is only here on 48, right? And on 0. So if we keep the last 4 on the cache, so those 4 here, then we will get hit for 48. And we will get miss for 0, and we will have one hit. But if we have 8 kilobytes, then those two will map to different sets, right? So in the first set, we will have 0. On another set, we will have 16. Here we have 32. This 48 will go here on another set. So those are basically two different sets. Yeah, so it is for 8 kilobytes. So if you assume 8 kilobyte cache, those addresses, I'm just showing addresses going to different sets. And then 64 goes here again, 80 goes here, 96 goes. Is it? No. 96 goes here, right? Yeah, 96 goes here, and we get hit for 48, but we also get a hit for 0, right? So we get 2 hits. Yeah. Do we need to give a break? What's the time? Okay, I think it might be good to have a break. And then we can continue with the labs, maybe, if you don't have any other questions about the homeworks. If you have questions about homeworks, we can also continue with that. But I guess some of you may have trouble with the software that we are using. So we thought it might be useful also to show how to set up the project and start working on the lab assignment. Okay, let's have a break for 9 minutes. Okay, let's start again with the your questions, if you have any more, any other questions. Actually, before that, I want to remind you that the deadline for the lab assignment is Tuesday night, but obviously there is a problem with the machines that we pointed to you that you can work on, the machines on the labs 26.1 and 3, I guess. So last semester we had the software Vivado installed on these machines, but it seems like it's gone, so it will need to be reinstalled. I'm not sure how much that will take. So first I want to ask if all of you can work on your machines, or do you necessarily need software to be installed? So how many of you have already started working on the lab assignment in his own machine, his or her own machine? You're working? You have a Mac. You're working on Mac?
It's on the original machine.
Okay, yeah, that makes sense. Do you need to be fast?
I don't know.
Okay. Yeah, so it will definitely be nice to have Vivado installed on these machines on the lab, so you can also maybe SSH to those machines and continue working from home. Probably will be faster than having a virtual machine. So we'll get it solved. So we will have the software installed back on those machines. Yeah, we'll let you know when it's installed, or maybe we'll point you to some other labs which already have the software installed. Okay? If you don't have any other questions about the homeworks, maybe we can show some stuff related to the lab. Okay. Who's going to do that?
Okay. So let's take a quick look at the Vivado software and see how to create. Maybe you are all familiar with this, but anyway, it can be useful for you. This is the first screen that we see when we open Vivado, and here we just have to create project. Click next. Let's call project pipeline, because we are going to open the pipeline that we are providing. RTL project. And now we add files. The files are user. They're here, right? Okay. No, we are not going to open the solution, sorry. Okay, so you add all these files to your project. Here you can see all the files we have selected. And that's all. Now we are initializing the project. You will see all the files you have added here in this source screen, in this sources tab, and the way they are connected to each other. So you know that the main file is testbench. In testbench we call the MIPS core module and also the memory module. That's what you have. So that's why here we have the MIPS core, and we also have the memory module. You need to also use the memory module because here somewhere, exactly in line 222, is where you have to include the DAT file that contains the program that you have previously generated using SPIM. Actually, you also have to add this program here. It's okay. And this is in the input. Actually, it's this one. We select all types of file, and here is our DAT. It's okay. Okay. Now finish. So you see the DAT file is here. Now if you want to run, you should know that you just need to click on Run Simulation. The simulation starts. It runs for 1,000 nanoseconds by default. You can see the timeline here. If you want to complete, in this case, the entire execution of the program didn't complete, so we have to run, let's say, maybe, for example, 1 more nanosecond. Is it running? Oh, yes, it ran for 150 nanoseconds more. And here you can see the output. Actually, this is the final state of the register file, and this is the total number of simulation cycles. I don't know if you have any questions.
So I'm not really sure how to debug with those tests. The register file or the output from the register we have in the end, should that be the debug information?
Can you help Mohammad with that answer?
For the answer.
Yeah.
So, what do you want for debugging?
Yes, like when I want to test if my cache works, to just compare the register file from the baseline with what I obtain when I insert my cache.
Yeah, exactly. You should load the value from the memory to the register, and then you can dump the register value and check the value. Yeah.
Is that okay?
Yeah, I think so. I mean, when I first, I didn't know that I had to run like for an additional 1,000 nanoseconds, so I only had the graph, and it's kind of hard to.
Okay, to see if it worked correctly or not. Yeah, you should extend the simulation until it completes. Mm-hmm.
Where will we insert our code? Which part?
Where do you insert your code?
Yes.
It's this here in MIPS mem file, line.
No. In the MIPS core. MIPS core mem.
Okay.
In this module, you should implement your cache.
Oh, here is where you have to insert your cache. Yes, that's true.
Am I correct that the cache is between or inside the mem control, inside the MIPS
Yeah, exactly. The cache should be before the memory controller. Yeah. And if the access is missed, then you should pass the address to the memory controller, and it takes time to access to the memory.
Like, there are a lot of wires to the memory controller. I'm not sure, do we need to handle all of those in the cache? Because like, there's some of them like write enable, but or for example, does the cache have to be byte addressable? Because it says the block size is, I think, 4 bytes, which would be the size of what the LAU operates on.
Yeah.
Like, do we have to handle like byte reads? Because it doesn't really say in the specification.
I'm not. I can check and let you know. Yeah, I should check. Okay.
Like, for example, the internal defines file, there are like special control signals.
Yeah.
The memory controller, for example. Will there be something similar for the cache? Or
Yeah, sure. Yeah, you can, for example, the number of tag bits, index bits, everything you can put in the that.
basically constants.
Yeah, the constants. Yeah, exactly. Yeah. Mm-hmm.
The size, so this is just something now
Yeah.
in the code.
Yeah, yeah.
It's not like some input.
No, yes, it's not input. Yeah. Yeah. For that, you mean the port name?
Yeah, and then wires as well.
Actually, the internal wires, you can do it as any names you want. But the names for the test bench module and actually the MIPS core and the memory, they should be fixed because we need to run these projects, your project and everyone.
Okay.
Yeah.
So I was looking at the signals that go in and out of the memory. So I know that, for instance, when it starts with mem, it's because it goes in and out.
Yeah.
And when it's in C, it's for the memory controller. But is there more? As long as it's consistent, it's okay.
Yeah, as long as it's consistent, it's okay. Yeah. Oh, you mean how to learn Verilog?
Well,
Actually, there is a book written by Samir Palnitkar. I think that's the best ebook, textbook for learning Verilogs. But there should be some online tutorials for learning Verilogs. It's very easy.
yeah, we can recommend maybe some book or tutorial. We will use Moodle to send a message to you all.
Yeah.
You can receive the name of the book.
Yeah, it's combination of logic. Yeah.
And then I noticed that some of the outputs have marked registered. So I don't know if I understand that correctly.
No, actually, reg in the Verilog, it doesn't mean the registers.
Yeah.
So actually, the reg in Verilog can be synthesized to a wire or in a latch or in a register.
Okay.
Yeah.
But what does it mean when you make an output like that?
Actually, it's a Verilog syntax. When you want to assign a value to a variable in the sequential statement, like always and initial in the Verilog, that output should be in a reg mode. So it's just a Verilog syntax. There is no specific reason for that. Yeah. No, no. What do you mean by the output of the cache?
The address, that if there is a miss,
Okay, yeah, yeah.
and also if it's a hit,
Mm-hmm.
and it might forward the data
To the pipeline.
to the pipeline.
Yeah.
Okay. Could you, I don't know, because there are so many signals over there, could you just briefly explain where does the cache, I mean, which signal shall the cache maybe probably connect to or something like that?
Some hint.
It should be somewhere between the, yeah, it goes down. Yeah, it should be somewhere between the definition of the module and the memory controller. Yeah, it's very easy.
Another thing, so for the actual cache stores,
Mm-hmm.
should we implement it? I don't know what the syntax is for implementing like a block.
No, no, it should be in the cache module, yeah. Yeah, your cache has a clock signal, and in the always statement, you can have always add post-age clock, and then you can write the value in the memory.
Okay.
Yeah.
But then, to implement this memory, is it just last time we did HDL and did stuff like this? It was just we made registers from
I know.
blocks, and then we just made a bunch of those. Is that the kind of thing that we should do here?
No,
or
no,
is
no.
there special-
Actually, the implementation of the memory is something like the register file. Could you?
Okay.
Yeah.
So-
Yeah.
Sure, yeah.
Could you go to the register module? Yeah, I think it's in instruction decode. Yeah. No. The MIPS register.
Oh, yes.
Please open the reg file underline report. Yeah. Okay. Yeah, you see, reg 31, 31. Yeah, it should be something like this. Yeah.
All right.
So is the baseline supposed to be synthesizable, the code that you provide itself?
Actually, the code we provided is synthesizable. Actually, the test mesh is not synthesizable, but other modules are, they can be synthesized.
So just
You also use the test bench, yeah?
That might have been the try to synthesize the test bench, so that's why it didn't work.
Yeah, actually, yeah.
so make sure that you select the proper modules as stock modules.
Like just the MIPS core.
Yeah, MIPS core and MIPS mem. Just MIPS core, yeah, because MIPS mem already has some. No. Actually, it's important to have the correct numbers, values in the registers, and also it's important about the simulation cycle, because in that way we can check that your cache is implemented through number of hits, miss, yeah. And actually the timing.
Also, one thing we want to tell you, because maybe I think that wasn't in the handout, is how are we going to evaluate the lab? So that's the first thing is, as Mohammad said, we will check that the output is correct, and we also will check the simulation cycles. And the other thing you have to know is that we will fix some slots for you to come to the lab and have some discussion with you, maybe like 15, 20 minutes, essentially because we want to make sure that you understood everything and that you did it yourself, of course. So that's essentially the idea. We will do this double checking. For these slots, we will probably use some wiki or similar tool in Moodle so that you can put your name in the available slots. That's how we will do it. Right. Yeah.
Okay, you should first go to MIPS mem. Go down. Yeah. And on the line 222, here you should change the name. Just select the first. For example, mem test. No, it should be mem test 0. Then you should remove or keep it.
Oh, we can keep it.
Yeah, we can keep it. You should add then just we should save it. And then if you simulate it, but you should put the test bench as a top level because.
Oh, yeah.
No, it is set as top. Okay, run simulation. The MIP score, yeah. Okay. The value of the registers is also dumped in a file. Here, as you see. But actually, if you want to do it correctly, this address should be absolute. It should be an absolute address. Yeah. Please change this address to an absolute, and then everything is fine. The command is run, and then you put everything you want, nanosecond. Actually, now we are running something that there is no code. So, yeah, we can run the simulation again if you want. Actually, after after dumping the register file values, if you run the program, nothing happens because there is no code in the memory. Mm-hmm.
There's a result of the output,
Yeah.
the register files.
Yeah.
This is what should we get after implementing our cache also.
Exactly, yeah.
Because we're not modifying anything to the execution.
Exactly. Just something different happen in the simulation cycles.
So we know what to compare ahead.
Yes, yes. Oh. Okay. I don't know. Do we have the infrastructure? She wants to do it remotely.
So working remotely was clock and the reset work exactly.
Okay.
Like I think this rises on the negative of the clock.
Could you point to that module that it has?
Like for example, mid-core mem.
MIPS core mem?
Yeah. Like line 99, for example.
Okay. Yeah, actually, sometime you will have the negage on the reset. So in the sensitivity list of the always is now if you have negage on the reset, you go through the always, and then you should check that this is because of the reset or this is because of the clock. Then exactly you see we check the reset value. So if it is negage of the reset, now the value of the reset is 0. So here we check the if not reset. So then we have some codes, some initialization because of the reset. And then if it is not reset in the else, this is because of the clock. What?
Like in memory, we store
Uh-huh.
on each clock cycle or the clock negative.
Everything, writing the memories or the registers is in the clock postage.
Oh, okay.
But I think reading from the register and also from the cache, and they don't need the postage clock. Actually, the reading circuit is combinational.